This video is the second video that addresses second-order non-homogeneous differential equations. The first video showed how to solve a limited number of these differential equations using what a method called undetermined coefficients. In this video, we will look at the method of variation of parameters. And the big advantage of the method of variation of parameters is theoretically, this method can be applied to any equation. And therefore, this method can be viewed as a solution to solving any differential equation of this form. That is a second-order, linear, non-homogeneous differential equations with possible coefficients that are not constant. So this is the outline of how we will be using the variation of parameters. So first, we find the solution of the corresponding homogeneous equation, and we'll get the complementary solution is equal to C1y1 of t plus C2y2 of t, where y1 and y2 are a fundamental set of solutions. This is one note when I told you theoretically we can apply this to any equation. So the first note is, so far we have shown how to solve the homogeneous equation only if it has constant coefficients. In other words, in front of y you might have an a. This p of t is a constant, it's not a function, and this q of t is a constant and it's not a function. This is our first example of where it might be difficult to use this method of variation of parameters. The second step is to replace the constant c1, c2 in our complementary equation by functions u1 of t and u2 of t. So here you can see I've done that now. I have y is equal to u1 of t times y1 plus u2 of t times y2. Next, I can take the derivative of y and I get y prime. For my third step, I'm going to choose an additional condition on the solution. The reason why I can do this is, as you have seen before, for solutions of differential equations, you get a whole family of solutions. You get an infinite number of solutions. So we have chosen to restrict our solutions using this condition here, that u1 prime y1 plus u2 prime y2 equals 0. And this condition was specifically chosen to make our lives easier down the line. This condition then simplifies our first derivative to only two terms, and then we can take our second derivative. The fourth step then is to take your y, your y1 prime, and your y double prime, and plug it in to your differential equation, which I have rewritten the differential equation here. And one thing you will see that this simplification has given us another simplification here when we plug this in. So if you've done all your algebra and your derivatives correctly, you will see somewhere in your, once you plug in y prime, and y double prime into your differential equation, you'll see that you have a y1 double prime term times p of t y1 prime plus q of t y1. And if you look at this here, because y1 is a solution to the homogeneous equation, this here is exactly the form of the differential equation with y1 plugged in. Since y1 is a solution to the homogeneous equation, all of this goes to 0. Similarly, you will see y2 double prime plus pty prime plus qty2. Again, that's exactly this differential equation. And since y2 is a solution of the homogeneous equation, that means this portion here goes to 0. This significantly reduces our equation till we get down to u1 prime y1 plus u2 prime y2 prime equals g of t. Again, this is what our final equation after we've plugged in y prime, and y double prime into our differential equation. And our last step, so what you see is now we have two equations. This last one we got from plugging in y prime, and y double prime into the differential equation. And this second equation over here that we chose as an additional constraint on our solution. So we have two equations, 1, 2, and two unknowns, the two unknowns being u1 and u2. So we can solve that system of equations, and what we will get is u1 prime is equal to y2 times gt all over the Wronskian of y1, y2. And u2 prime will be equal to y1 times g of t all over the Wronskian of y1, y2. So now we have two equations of u prime and u2 prime, so we can integrate with respect to t to get u1 and u2. And the last thing we have is this theorem for variation of parameters. It's considered the non-homogeneous second-order differential equation y double prime plus pty prime plus qty equals g of t. If the functions p, q, and g are continuous on an open interval I, and if the functions y1 and y2 form a fundamental set of solutions of the corresponding homogeneous equation, then a particular solution of the non-homogeneous equation is capital Y, that's our particular solution of the non-homogeneous equation, is denoted with a capital Y of t, is equal to negative y1 integral from t naught to t y2 of s g of s all over the Wronskian ds plus y2 integral from t naught to t y1 g all over the Wronskian. With this theorem, that means you can, for the method of variation of parameters, you can follow these 5 steps here to get a solution, or you can go directly to the theorem and plug into the formulas. For each of our examples, we will use both methods. I have summarized the procedure for using the variation of parameters to solve the second order linear non-homogeneous differential equation, and we're going to look at an example to find the solution of y double prime plus 4y equals 8 tangent of t, where t goes between negative pi over 2 and pi over 2. The first thing to note is this is not a good candidate for undetermined coefficients, which is a very straightforward way of solving an equation and probably the first thing I would try. However, we can use the undeterminate coefficient method for sines or functions where g of t has sines and cosines and products of sine and cosines. However, tangent is a quotient of a sine and cosine, so that won't work. The first step is to solve the homogeneous equation. So I have the equation y double prime plus 4y equals 0, and this is the corresponding characteristic equation, which gives us r is equal to plus or minus 2i, and if you recall, that would give us e to the 2it, and from Euler's formula, we see that that means our complementary solution is c1 cosine of 2t plus c2 sine of 2t. Remember, e to the I u of t is equal cosine of ut, I sine of ut. In this case, u of t is 2t. Now I can calculate the first derivative as well as the second derivative, these two quantities here, and I can verify that I have a solution to my homogeneous differential equation. From the first step then of solving the homogeneous equation, I have the homogeneous equation here, and I have the complementary solution is equal to c1 cosine of 2t plus c2 sine of 2t. My next step is to replace the constant c1 and c2 in this complementary solutions by functions u1 and u2, and that is what I've done here. I have y is equal to u1 cosine 2t plus u2 sine of 2t. Then I can take the derivative, which I have written out here, and then I grouped my non-derivative u1, u2 terms together, and then I grouped my derivative u1, u2 terms together over here. And what I have is y prime of t is equal to minus 2u1 sine of 2t plus 2u2 cosine of 2t plus u1 prime cosine 2t plus u2 prime sine 2t. When we come to step 3, we're going to impose this additional constraint. The u1 and u2 prime terms will have to, when they have to add together to equal to 0. So these last two terms, which is why I kind of reordered these, so these last two terms are the ones with the primes, the u1 prime cosine 2t, u2 prime sine of t. These added together go to 0. The idea about adding this constraint here is before we add the constraint, we have one equation and two unknowns, the two unknowns being u1 and u2. And when we have one equation and two unknowns, our system is undetermined and we will have an infinite number of solutions. Sort of, in linear algebra, or if you just look at the equation of a line, y equals mxb, if you have two unknowns, y and x, then if you only have one equation, right, you can choose an infinite number of values for x and then get a corresponding value for y. So this is, one equation, two unknowns. Similarly here, you have one equation, two unknowns. It's not a linear, it isn't linear. One equation, two unknowns. So you have an infinite number of solutions. So we can impose a second condition. And this is the second condition we impose, that the terms with the primes equal sum together to be 0. And this condition was given to us by Lagrange, and it was chosen to make our life easier down the road. And why can we do this? Can we just throw in random conditions? Well, yes, we can. So you're familiar with, let's say we had an equation with three unknowns, or we had two equations, three unknowns, and we solved it, and it came down to x1 is equal to minus x3, and x2 is equal to 1 minus x3. Again, it's an infinite number of solutions because we can have an infinite number of values for x3, but once we choose x3, x1 and x2 then we could solve for. So often what I would do if I were asked to find a solution to this is I would choose x3 equals 0, and then my x1 would be equal to 0 and x2 is equal to 1. And therefore I have found a solution. That's the same thing here. Oh, and also the other thing is, when you're teaching someone beginning algebra, they'll ask, well, why did you choose x3 equals 0? And you'd say, because it's an easy number to work with, right? If I chose x equals 1,000 and this had fractions, it'd be, or not, 995. These equations might not be easy to work with, but x equals 0 simplifies things. That's the same exact thing we're doing here. We have an infinite number of solutions, so we decided to limit our solutions by putting this additional constraint, sort of the way we chose x equals 0, and we chose the constraint in a way to make our calculations later simpler. And I just want to be super clear. These equations in blue, this y equals mx plus b, and this x1, x2, x3 example, they have nothing to do with our problem here that we're doing in differential equations. I only threw them up to illustrate how it's okay, well, one, how we have infinite number of solutions, and then two, how it's okay to throw in an additional constraint and to choose that constraint to make our calculations easier down the line. So again, I have an infinite number of solutions, so I added this additional constraint, and Lagrange is the person who showed us a constraint that will make our calculations easier down the road. This additional constraint will then further simplify our y prime, which I've rewritten here. So it's minus 2u1 sine 2t plus 2u2 cosine 2t. Then we can take our y double prime, which is 4u1 cosine 2t minus 4u2 sine 2t minus 2u1 prime sine 2t plus 4u2 prime cosine 2t. Now we can plug in our y prime, and our y double prime into our differential equation, which is y double prime plus 4y equals 8 tangent t. So I've plugged it in here. I won't read it all out to you, but the whole equation is equal to 8 tangent t. There are a couple of things that can cancel out. This u1 cosine 2t can cancel with this 4u1 cosine 2t, and this minus 4u2 sine 2t can cancel with this 4u2 sine 2t. So what we're left with, after we plug in our y prime and y double prime into our differential equation, y double prime plus 4y, is minus 2u1 prime sine 2t plus 2u2 prime cosine 2t is equal to 8 tangent t. So if you've done all your calculations correctly, at the end, your differential equation, you should end up with u1 prime terms and u2 prime terms. You shouldn't have any more u1s or u2s without primes. Here I kind of summarize things. I put my y prime here. I didn't copy down y double prime, but I did write what y double prime plus 4y is over here. And what you notice is we have two equations now. The first one came from our Lagrange, a different additional constraint that the prime u1 and u2 prime terms sum to 0. And then we have the second equation that comes directly from our differential equation. So now we have two equations and two unknowns, our two unknowns being u1 and u2. And from here, the algebra, the trig, the integrals, they get a little messy, but that's really all it is. Like, this is the stuff that you've known how to do since first year calculus. It is a little messy, so we'll go through it. It's easy to start. You have this equation here, so we can solve for u2 in terms of u1, or rather u2 prime in terms of u1 prime. And now we can rewrite this equation here, but substituting for u2 our u2 solved in terms of u1. So what we'll end up with is our minus 2u1 prime sine of 2t, and then our substituting u2, we get minus 2u1 prime cosine 2t sine of t, and this cosine squared came because we need to multiply by another cosine 2t term, and that will all equal to 8 tangent of t. This next step is just algebra. I pulled out my u1 prime of t, and then I'm left with my minus 2 sine 2t and my minus 2 cosine squared t over sine t, and that's equal to, pulling out, I still have my u1 prime out here, and I put this over the same denominator as sine 2t. So that gives me my minus 2 sine squared 2t plus my cosine squared 2t over sine 2t, and that's equal to 8 2t. And again, some more algebra, some more trig. So from here, my sine squared and cosine squared is equal to 1, so I'm left with 2 on the top and sine 2t, and that's equal to 8 tangent of t. So I move this over to the other side, so I have u1 prime is equal to 8 tangent t, sine of 2t over minus 2. These two can cancel out and get me a minus 4. And then with the sine 2t, I used my double angle formula because that will allow me to kind of simplify this sine and cosine. So my double angle formula will give me my sine 2t is equal to 2 sine of t cosine of t. Converting my tangent to sine over cosine, I simplify this till I finally get u1 prime is equal to 8 sine squared of t. And I had to summarize and move everything up to give myself more space. So again, we have our differential equation, our y prime. We plugged in y prime, and y double prime into our differential equation here. We had our extra condition for our solution. So we have two equations, two unknowns. We solved for u2 in terms of u1, and then or u2 prime in terms of u1 prime, and we just figured out that u1 prime is equal to 8 sine squared of t. I have a couple of double angle formulas again that we're going to use. So plugging in u1 prime into u2 so we can figure out what u2 prime is, we have u2 is equal to 8 sine squared of t times cosine 2t over sine 2t. Now we're going to use basically the double angle formula on both of these, on the cosine 2t and also on the sine 2t. My cosine 2t by my double angle formula is going to equal to 2 cosine squared t minus 1. My sine 2t, again by my double angle formula, is going to be 2 sine t cosine t. From here to here is just algebra. I canceled out one of the sine t's, and I'm left with 1 sine t on top, and then my 2 cosine squared t minus 1 remains unchanged, and my 2 cancels with this 8, so I get a 4, and then I'm left with cosine on the bottom. And then again, just algebra. I pulled out my sine and put it with my 4, and then divided each of these terms by cosine. And here again is our summary slide updated with our equation for u2 prime, and here is our equation for u1 prime. And now we are really close to figuring out u1 and u2, because what we need to do next is integrate. I have written my formula for u1 prime here, and I integrated both sides of the equation using my half angle formula for sine squared, and this 1/2 I canceled with the minus, or simplified with the minus 8, so I have a minus 4, And then using my half-angle formula, I have 1 minus cosine 2 theta. When I integrate, I get minus 4t minus 1/2 sine 2t, which I need to add the c. I just kind of multiplied everything out. I forgot to add the c over here, but I added it here. And then using my double angle formula, which this is an extra step you don't have to do, but just in case you're checking your answers, I have this in two forms, converting my sine 2t into my sine cosine. So either of these would be acceptable as an answer for u1 of t. Similarly, for u2, I have my equation for u2 prime, and I integrate both sides of the equation. Over here, I already did some simplification. I pulled out my 4. I multiplied my sine times cosine. I multiplied my sine times 1 over cosine here. And the rest is fairly straightforward integration. I have my 4. This gives me my 1/2 cosine squared t, but I simplify with the 2, so I get my minus cosine squared t. And here, this is just tangent. The integral of tangent is natural log of cosine of t, and then with my integral, I put a plus c at the end. And it's great now. We have u2 and u1 solved for, but remember many minutes ago when we started this problem, the solution to the particular equation is u1 cosine 2t, u2 sine 2t, plus the solutions to the homogeneous equation. This was just when this wasn't the capital Y, this is lowercase y, but we were substituting u1 and u2 for c1, c2. So the capital Y, and I don't have that written here, the capital Y, again, is u1 times y1 plus u2 times y2 plus c1 y1 plus c2 y2. And this is our final solution, the particular solution for this non-homogeneous equation. We also have this theorem that kind of summarizes all of this and just cuts to the chase. So if we have a non-homogeneous second-order differential equation of this form, y double prime pt y prime plus q t y equals g of t, if the functions p, q, and g are continuous on an open interval I, and if the functions y1 and y2 form the fundamental set of solutions of the corresponding homogeneous equation, then a particular solution of the non-homogeneous equation is capital Y of t, and then we have this formula, negative y1 of t integrated from t naught to t, y2 times g over the Wronskian, plus y2 times the integral from t naught to t, y1 times g over the Wronskian. So again, this theorem cuts to the chase and tells you exactly what the particular solution will be. Also, when where t naught is any conveniently chosen point in I, the general solution looks like c1 y1 plus c2 y2. These are this fundamental set of solutions, plus our particular solution given to us here. So let's redo the last problem using this equation just for comparison. So here's the same problem, y double prime plus 4y equals 8 tangent of t, and here's the solution. I did kind of redo the solution a little bit using half-angle formulas and double angle formulas, sines, cosines. And this, so I transformed it a little bit, or I altered it a little bit, but this is the formula we want to verify. When we worked this problem using the long procedure, not just the shortcut kind of theorem straight to the formulas, and actually this actually still gets quite involved. But when we worked through the method of variation of parameters, we had solved the homogeneous equation, and we got the solutions y1 is equal to cosine 2t and y2 is equal to sine of 2t. So because we need the Wronskian, that's what I calculated next. So I have our first solution, cosine 2t, our second solution, sine of 2t, then the derivative underneath, which is minus, of cosine 2t is minus 2 sine 2t, the derivative of sine 2t is 2 cosine 2t, taking the determinant, so cross multiplying, I get 2 cosine squared of 2t, and minus the multiplication here gives us plus 2 sine squared of 2t, our cosine squared of 2t and our sine squared of 2t added together gives us 1, so we're left with 2 for our Wronskian. I started to plug things into my formula for my particular solution, capital Y of t. I have my negative y1, that's my negative cosine 2t, times the integral y2 times g. So y2 is sine of 2t times g, 8 tangent s. Oh, and my variable of integration is s. So I switch that all over the Wronskian, which is equal to 2, plus, and now I do my y2, the sine of 2t times y1g. So y1 is cosine 2s, my g is 8 tangent s, all over the Wronskian, which is 2. Next, I combine my 8 and my 2, which will give me 4, and I move it outside. And I'm left with sine of 2s, and then I converted my tangent to sine over cosine. Same thing, 8 and 2, I moved it out, so I have my 4 sine of 2t, and then I have my cosine of 2s, and then my tangent I converted to sine and cosine. The next thing I use are my double angle formulas for this sine 2s and this cosine 2s. So for sine 2s, I get 2 sine s cosine s times sine over cosine. So the cosines cancel out, and I'll be left with 2 sine squared s. Over here, I have my 4 sine 2t. Then I use my double angle formula on cosine 2t, and I get 1 minus 2 sine squared s. And then I need to multiply by sine s cosine s. So the sine s cosine s times 1 is over here, sine s cosine s. When I multiply here, I get my 2 sine cubed s cosine s. Here is where we last left off, and I'm going to now, because I have this sine squared, I'm going to apply the half angle formula. So my sine squared is going to become 1/2 1 minus cosine 2s. So my 1/2, cancels with this 2, so I have 1 minus cosine 2s. That's this part here. Now I still have my 4 sine of 2t. This I just went ahead and made into tangent s. Here, my sine cubed. So when you have an integral of odd powers of sine and odd powers of cosine, what you can do is break apart your sine into sine s times an even power of sine. Then this even power can be 1 minus cosine squared s. So that's where this part of this line comes in. For these two, I went ahead and integrated. So here I have my minus 4 cosine 2t. I integrated this with respect to s and then plugged in t naught and t, and I get t minus 1/2 sine 2s plus 4 sine of 2t. You could integrate tangent of s, and you get natural log of cosine. I still have this integral to do. Here is where we left off. We had done the integration over here, and we did the integration here, and we're left with this last integration, the 4 sine 2t, and this one here, where we had broken off the sine squared, so it's 1 minus cosine squared. So now we can integrate this. Is that true? Let me see. But first I took the minus 2, combined it with the 4, and I get minus 8 sine 2t, and I have the integral, I see what I'm doing, multiplying sine s times 1 over cosine, I get my tan s again, and then multiplying sine s times cosine squared, I get sine s, and then this cosine squared will cancel with this cosine, and I get sine s cosine s. Again, carrying these numbers down just verbatim, I still have my 8 sine 2t. My integral of tangent s, again, is natural log of cosine t, and now this I can integrate, and I still have my, I still have to multiply by 8 sine of 2t, but this integral is 1/2 cosine squared of t, so the 1/2 factors in with the 8, and you get minus 4 sine of 2t cosine. This part is cosine squared of t. So this is where we left off, and the rest is algebra, and like here we have the trig, half angle formula, other manipulations to get it look like the solution I had before. So we've done one problem both by kind of using the steps for the variation of parameters as well as the theorem which gave us the formula. We'll do one more problem. I start step 1, find the general solution of the corresponding homogeneous equation. So here's my differential equation. I have the characteristic equation which gives me r is equal to minus 2. When you have a single root, then y1 is equal to e to the minus rt, and y2 is equal to t e to the minus rt. Step 2, replace the constant c1 and c2 in our, well, I don't have it here, in this general equation here with u1 and u2. So I'm going to have y is equal to u1 times y1 plus u2 times y2. Then I can go ahead and take the first derivative of y, which I have here, which is minus 2u1 e to the minus 2t plus u1 prime e to the minus 2t plus u2 prime e to the minus 2t plus u2 times minus 2t e to the minus 2t plus e to the minus 2t. And remember, here we chose an additional condition on the solution that the two terms with the derivative added together will equal 0. So here's my u1 prime, here's my u2 prime term. These two added together will go to 0, which simplifies our y1 term to negative 2u1 e to the minus 2t plus u2 times minus 2t e to the minus 2t plus u2 times e to the minus 2t. Then we can calculate y double prime, which is equal to minus 2u1 prime e to the minus 2t plus 4u e to the minus 2t plus u2 prime times minus 2t e to the minus 2t plus e to the minus 2t plus u2 times 4t e to the minus 2t minus 2e to the minus 2 minus 2e to the minus 2t. And I cheated a little bit. I took this equation from the detailed instructions on the method of parameters just to see, where did I take it? From here, where I had y1 and y double prime. And I stuck it here so that after I did this long calculation, I could just kind of verify that it has the same form. This isn't something you have to do. I just found, because this calculation was so long, I wanted something to kind of double check things before I continued. Step 4, I plug in my y prime and my y double prime into my differential equation. So here is my y, and I combine these two. I copied it straight from here otherwise. Here is my 4y double prime. That's this portion here. So I multiplied by 4. And then my 4y is this term in parentheses. And now I took this part of the details of my method of variation of parameters, and I stuck it here to remind me that all of this stuff should cancel out except for the u1 prime and the u2 prime terms. So I shouldn't be left with anything for u1 and u2 because this part of the equation, since y1 and y2 are solutions to the homogeneous equations, these should go to 0. So I'm going to see what cancels out over here, and hopefully I'm only left with u1 prime terms and u2 prime terms. First, I'm going to look for my u1 terms because I don't want them in here. This is the first one I have, 4u1 e to the minus 2t, and I have another one over here, 4u1 e to the minus 2t, but that will cancel with my 8. So these two will cancel with this, 8u1 e to the minus 2t. Now I want to look, let's see, here I have u1 prime, so that's good. I have a u2 prime, that's good. I want to look at my u2 term. So first I have a 4t e to the minus 2t. So I'm going to look for forms of 4t e to the minus 2t. I see one here, so but these add, so I have 8t e to the minus 2t, but here I have a minus 2 minus 4. So these three will cancel out. So I'm going to kind of cancel this, so that's 8 with this, which is my minus 2 times 4. And I still have this u2 minus this minus 4e to the minus 2t, but that will cancel with this one here. So I have this canceling with that. And so if you look, all I have left are my u1 prime, my u2 prime times something, and everything canceled out, which is exactly what we want. And just kind of rewriting this, I have my minus 2u1 e to the minus 2t, and my u2 prime 2t e to the minus 2t plus e to the minus 2t, and that is equal to, if you recall, the other side of the equation, which I didn't bother writing over here because I was running out of space, but it's equal to t to the minus 2 e to the minus 2t. I feel like now we've made a lot of progress. I also want to mention, if you get to this step, and when you cancel stuff out, if you're left with any u1 or u2 terms without the prime, if there's a u1, then something went wrong. All the u1 and u2 terms should cancel out. You should only be left with primes. That was part of why this solution here was chosen by Lagrange. It was to get rid of those so that then we don't have another differential equation to solve. I mean, we do, but all we'd have to do is integrate. And this is where we are so far. We have our original equation, our characteristic equation, and our solutions to the homogeneous equation. Then we took the complementary solution and we placed the C1 and C2 with the U1, U2. We took our first derivative, our second derivative, we plugged y prime, and y double prime into our differential equation, and then we eventually got down to this equation that we had on the last slide. And this here comes from our assumption. Our second equation is the u1 y1 plus u1 prime y1 plus u2 prime y2 equals 0. And solving for u2 in terms of u1, I get u2 prime is equal to minus u1 prime over y1, y2. So again, we have two equations here and two unknowns, the two unknowns being u1 and u2. From here on, everything is kind of algebra, maybe trigonometry and stuff you learned from first year calculus. Not to say that it's difficult or easy, because like I make, I can't tell you how long I took chasing down algebraic errors. But anyway, here we have our two equations. So into this equation, I could substitute for u2, I can substitute u1. So I have my equation minus 2 u1 prime e to the minus 2t. And then for this u2, I substitute minus u1, y1 over y2. So that's e to the minus 2t, t e to the minus 2t. Again, my y1 and y2 are here. And then I multiply by my 2t e to the minus 2t plus e to the minus 2t. And that's equal to this right-hand side of our differential equation. And then a little more algebra to simplify this part of the expression. And now a little more algebra. I combine these terms and I get u1 prime e to the minus 2t times t to the minus 1 is equal to t to the minus 2 e to the minus 2t, moving the e to the minus 2t over, it's really, and the t minus 1 over, it kind of simplifies really well, so that minus u1 prime is equal to t to the minus 1. Integrating both sides, I get u1 is equal to the natural log of t plus c. Barring any algebraic errors or dropped derivative signs, we're practically done now. Our last step, u2 prime, where is this, is equal to minus u1, u1's over here, so we have a t to the minus 1, y1 over y2. So here we have y1 over y2, which is equal to 1 over t squared. These two combine. And then you integrate both sides and you get u2 is equal to minus t to the minus 1. So this is our general solution. It is our u1 times y1 plus u2, where's u2 here, times y2. So the t to the minus 1 cancels with this t. And then we have plus c1 e to the minus 2t plus c2 t e to the minus 2t. These can kind of combine, so we have natural log of t e to the minus 2t plus c1. And I said we would do this both ways, both by doing all the steps of the variation of parameters, as well as using this straightforward formula. And in this case, the formula is actually quite relatively quick. Here is the same problem. My y double prime plus 4y prime plus 4y is equal to t to the negative 2 e to the minus 2t. And here is my formula. We solved our homogeneous equation to get these two fundamental set of solutions, and now we can calculate the Wronskian, which is used as the denominator for both. So here I have y1, which is e to the minus 2t, and then I have y2, which is t e to the minus 2t. I take the derivative of y1, I take the derivative of y2, I do the cross multiplication, with the minus over here, and this simplifies to e to the 4t. just to give myself a little room, I kind of moved my e to the 4t over here. So now I can plug into my equation. I have minus y1 of t, which is e to the minus 2t, integral of y2 times g. So y2 will be, and again, with respect to s, because that's our variable of integration, will be s e to the minus 2s. So here I have s e to the minus 2s, and then my g, s to the minus 2 e to the minus 2s, all over my Wronskian, which is e to the minus 4s. And then I'm going to add that to my y2, which is t e to the minus 2t, and then I'm going to integrate using s as my variable of integration of y times g. So y is e to the minus 2s. My g is still s to the minus 2, e to the minus 2s, all over my Wronskian, which is e to the minus 4s. Some algebraic manipulations, some integrals, and you will find that your particular solution is e to the minus 2t natural log of t minus 2 e to the minus t, which is exactly what we found using the other method. And then I also just wrote down the general solution as well. In this problem, I feel like the formula here given by the theorem was definitely a big time saver. So in this video, we looked at the method of variation of parameters. It was the second way of solving non-homogeneous differential equations, in particular second order, linear, non-homogeneous differential equations with potentially non-constant coefficients. I can remember that word. Okay, so in principle, this can be applied to any equation. These are the steps for our approach, and the first step is to find the general solution to the corresponding homogeneous equation. And so we get our complementary solution is equal to c1y1 plus c2y2. The next step is to replace the constant c1 and c2 by functions u1 of t and u2 of t. So now we have y is equal to u1 of t, y1 of t plus u2 of t, y2 of t. Then we can take the derivative of y with respect to t. And the next trick is courtesy of Lagrange, and you have to really appreciate the brilliance of this trick, and you'll see that later when all this stuff cancels out. But he said, well, at this point, we can choose an additional constraint so that our terms with the primes, the u1 prime and u2 prime, when we add them together, it equals 0. That will simplify our y prime here to things without u1 and u2 prime. So we have u1, y1 prime, u2, and y2 prime, and then we can take the second derivative. So the next thing here is that we can plug in our y, where's our y? Our y prime that we calculated, and our y double prime into our differential equation. And then what will happen, because of this brilliant equation or condition that Lagrange put on there, is that all of our u1 and u2 terms will go to 0, because what you'll get if you just work this out for the general, not just a particular equation, but with the variables in there, what you'll see is you'll have a y1 double prime plus pt y1 prime plus q of t y1. This here, because y1 was a solution to the homogeneous equation, this part of the differential equation with y1 plugged in will go to 0. Similarly over here, the y2, because it was a solution to the homogeneous equation, this part of the differential equation with y2 plugged in goes to 0, and that eliminates the u1 and u2 terms, and we're only left with the u1 prime and u2 prime terms, which in particular is u1 prime, y1, u2 prime, y2 prime. And now we have two equations, two unknowns. This equation here that we got when we plugged y prime, and y double prime into our differential equation, which I have written here, as well as this condition that we imposed that our u1 prime and our u2 prime terms would equal sum to 0. Two equations, two unknowns. At that point, it's algebra, maybe some trig, and then an integral. And this was, so then we plug it in, we integrate with respect to t. Then we also had this formula. So instead of following all these steps, we can plug straight into this formula. So if we have a non-homogeneous second order differential equation of this form, y double prime plus pt y prime plus qty equals gt, if the functions p, q, and g are continuous on an open interval I, and if the functions y1 and y2 form a fundamental set of solutions to the corresponding homogeneous equations, then a particular solution of the non-homogeneous equation is right here, where t is any convenient point, and the general solution is y is equal to c1y1 plus c2y2 plus capital R particular solution y. There are not that many key ideas here. The first one is to replace your c1 and y1 with functions of u1 of t, u1 and u2. You just straightforward do the calculations for the derivatives, plug into your equation. Except that the second thing you want to remember is this condition here that Lagrange gave us. Plug it in, then remember that once you simplify everything, you should only get things with derivatives. The key here is not to remember this equation, but to remember if you've done all your calculations correctly, if you're good at algebra, then, and also taking your derivatives, which actually is algebra at some point. If you've done all your calculations correctly, your u1 and u terms should go away, and you're only left with u1 prime and u2 prime terms. Again, it's not the equation that's important, but that the u1 and u2 terms should go away. And then you have a system of equations, and from there, it really relies on your algebra and you do your algebraic manipulation, so you solve for u1 prime and u2 prime, and then since you have u1 prime and u2, you integrate to get u1 and u2. So after a while, the calculations seem like a lot, but don't let those overwhelm you. Just remember those three kind of key points. Okay, that's it for this video. Thank you for watching.